Hey, welcome. Today we're going to be using some specialized pieces of equipment. This is called a light table. I know it doesn't look like a table at all, or maybe a light track. What it is a ruler based on things that we can pop in. And what's really cool about when you pop them in is right in the middle there, it tells you exactly where you are on the table. And this is also where we're going to be measuring from. So for example, this particular piece of equipment, I just pulled it out, it is a mirror. And as you can kind of see, it looks like a mirror. This happens to be the concave mirror.
I see myself in there.
Well, you're never supposed to see the cameraman in the movies because it just takes away the magic of it. And this is the convex mirror. This is when, like, you're thinking about shoplifting in the store, but you look up and you see that mirror? Yes, okay. And what it is, they also say what it is there. This is I need excuse me, my own personal lenses, my old man reading glasses here. This is a 50 millimeter concave mirror, 50 milliliter FL focal length. That's going to be important in our equations later. Now, this is a really important thing. This is what we are going to use as our light source. And we're going to actually set this in the track, and the way that it is there's a little cut right here, and we're going to put this little cut right at 0 centimeters because we're going to determine distance from the object. And guys, this is always going to be your object. If I were to look at anything, if I were to look at Dr. Johnson, you know what, I'm not really looking at Dr. Johnson. What I am looking at is the light that is being reflected off of Dr. Johnson. And then my psychology says, whoa, that's what Dr. Johnson looks like. I don't want to get into philosophy or anything like that. But he is the object that I'm looking at. And so how far away Dr. Johnson is like the distance of the object. Okay. So if I have something 40 centimeters from this is the distance of the object. If this is the mirror, and if I put a mirror at 40, well, then the distance the mirror is from the object is the distance between 40 and 0. Cool. But what the mirror is going to do is the mirror is going to create an image. Now, how am I going to see the image? This is funky. This is a half screen. Only half of it. Why isn't a full screen? Well, guys, if it was a full screen, my hand is a full screen, absolutely no light can get to the mirror. Therefore, absolutely no light can bounce off the mirror, and that's rather boring. Okay, why is it an empty screen? Well, guys, this is an empty screen and there's no place for the image to form, so we can't see it. So what we're going to do is we put a half screen somewhere. And what side do we look on the half screen? Well, the light goes through the half of the screen that isn't a screen, hits the mirror, reflects off of the mirror, hits the part of the screen that is a screen. And what we're going to do is, and we're going to look at this later, you can trust me right now, we're going to move it back and forth until it's focused. Let's say it's focused right here. And you're going to be later seeing it focus, okay? Now, what is the distance that the image is from the mirror? What we care about is the distance from the mirror. Remember I talked about the distance of the object was 40? Well, yeah, the object is 40 from the mirror and the mirror is 40 from the object. But what we care about is how far things are away from the mirror, later on from the lens. So my screen is 25 away from my object, but it's 15 away from the mirror. 0, 25, 40. What we care about is this 15 right here. Okay. Later on, we're going to start off, it's going to be like 30 and 15. And yeah, this guy's going to be 15 away from both of them. But what we care about when we say D image, it's how far away we are from the mirror and or the lens. Real important. Positive and negative distances. If we're talking about mirrors, anything in front of the mirror is positive. And if you think about it, where do you stand in relationship to a mirror? Have you ever stood behind a mirror? Can you see yourself very well behind a mirror? Have you ever taken a picture of yourself behind a mirror? No! Always in front. So anything in front is positive. Can images form behind a mirror? Yeah, they actually can. It's kind of freaky. And we'll look at that a little bit later. Any image that forms in front of a mirror is called real. I know it's an oxymoron, a real image. Any images that actually form behind the mirror are called virtual. We'll look at that a little bit later. Okay.
So we actually have some larger scale versions of the mirrors that Professor Ashcraft was just talking about. This one, the edges of the mirror, the outer edge is closer to you guys, closer to the camera, than the middle of it. The middle is like bent in. It's sort of like a cave, sort of concave. Can you see Professor Ashcraft in there? Look at that. Right side up or upside down?
That's right, upside down.
So what if I get real close?
Ooh.
Oh man, it probably got blurry, and I hope if I was able to get close enough, it flipped over. It was right side up. So that's kind of a cool feature of the concave mirror. Over here.
So can you do that with a spoon also?
Yeah, in my pre-lab video, you probably saw it. There's a spoon that I flip over. This is the bowl part of the spoon, but if you flip that spoon over, you look at the back, the middle part is closer to you than the edge part. The edge part's like sinking back. There's a convex mirror. And right side up, I believe you see Professor Ashcraft in there, nice and right side up. And as close as I want to get, doesn't matter, always right side up.
And I'm always smaller too.
Yeah, but it gives a big field of vision, right? You can see like the amount of image that you can see. It gives you a wide range, which is why you put them up in the corner of a convenience store. You can see a lot of area of the store.
You see those in hidden driveways a lot also.
Yep.
So that way you can, so you don't get in accidents.
Look around the corner.
Cool.
Awesome.
Guys, I had one last thing I wanted to show you about the object. Now, I want you to notice on the object, you have two arrows. One is pointing straight up. The other is pointing to my left. Probably to your right. Okay. Now, there's also a little, there's two circles. The outer circle turns out to be 20 millimeters in diameter, or 2 centimeters in diameter. The inner circle turns out to be 1 centimeter in diameter. This way, we can measure the magnification. Now, one question is it positive magnification or is it negative magnification? If the image is upside down, like I was in the, like you'll see sometime in some concave mirrors, the arrow that's pointing up is going to be pointing down. If the arrow normally points to the right, it'll point to the left. Or if it points to the left, it'll point to the right. If something says Fermilab on it, it'll read, I don't know what it'll read, but it'll be backwards. Okay. The other thing is, if you actually measure your image, you can see if it's bigger or smaller. For example, if I were to take a ruler, I have a ruler somewhere here, and measure this, the outer circle would be 20 millimeters or 2 centimeters. But if my image is, say, 4 centimeters across, well, that's twice as big. If my outer circle is half a centimeter across, well, that's 1/4 of the size. So we can actually measure the magnification by physically measuring the distance and also noticing if it's upside down or right side up. Okay, I think it's time to get to work. I'm going to put this exactly at 0 on the ruler just to make the life easier. Okay, people, doing the lenses, it is very similar to the mirrors. The object is same as it ever was, and we're going to have it at 0. We have a couple different lenses. Now, one thing about the lenses is you can actually see through them. And I always think that the purpose of a mirror is to reflect light. The purpose of a lens is to actually have light go through. For example, I use lenses to help me read or to help me drive. Light goes through them. The purpose of a lens, if I'm looking at Dr. Johnson, again, he's the object. I don't see Dr. Johnson, I see the light that is reflected off of him. I want the light to go through these lenses, in fact, go through the lenses of my eye, to hit the back of my eye and the retina in order for the impulses to go up to my brain and the psychology saying, hey, that's Dr. Johnson. So for positive distances, let's say I'm going to put this lens at 40 centimeters. If my object is on the left side, the distance the lens is from the object is 40 centimeters. That's positive. If the object is ever on the other side, it's going to be negative. Can that happen? We're going to see later that if you have two lens combinations, it actually physically can't happen. And I say to myself, well, the light is supposed to go through the lens. So anything on the other side of the primary object, I'm going to make positive for the image. This is different than the mirror. Okay. Can I have images form on this side, the same side as the primary object? And the answer is yes, especially if you have lenses that don't converge, but if they diverge. And if that happens, then you have a virtual image. You can't actually go back there and take a picture of it. Can't collect light there. But if light goes through and focuses on the other side, in fact, what we do is we have a viewing screen that we actually adjust back and forth, which you'll be doing, and we'll be doing too, and we'll actually figure out exactly where it focuses. And the distance the image is the distance from the mirror to where it focuses. Now right now I said that it focused at 94 centimeters. Well, my lens is at 40. So the difference, I'm going to say that my DI, the distance of the image, is going to be 54 centimeters, that difference. So that's how we're doing that. All right, so for the first one, what I'm going to do is I'm going to set P at 15. And P, again, is the distance the mirror is from the object. The object's at 0. So I'm going to put P right at 15. You can't see it, but the middle is right on 15.
Sometimes Dr. Johnson likes DO and DI, but you might also see P's and Q's.
Yeah, I'm not sure what your lab manual actually has.
Sometimes you'll see S and S prime, but they all mean the same thing.
Yes. Okay, so what I've done is I put the screen half, somewhere in the middle here. And again, what I'm doing is I'm looking on this side because I want to see the light that hits the mirror and then bounces onto the screen. So I'm moving it kind of gently. Okay, I'm starting to get something in focus. Now, one thing that you can see is that the edges here are looking more and more sport. Whoops, that's too much. Okay, let's go back. You know what? I'm going to turn my computer off. And maybe that might help you guys in the camera see just a little bit better. Okay, now you got to remember I got old man eyes, but that looks pretty gosh darn good.
Yep.
Okay. In fact, if it just goes wiggle a little bit back and forth, the image is going to get a little bit shaky. Okay, now my reading on the scale is 7.5 centimeters. Question is for the DI. Is it because I'm 7.5 centimeters away from 0? Or is it because I'm 7.5 centimeters away from 15? The DI, again, remember, is the distance away from the mirror. So I'm going to do 15 minus 7.5 centimeters. And I'm going to get 7.5 centimeters. Okay. My next question, I think, is the height. Maybe is it upside down or not? Oh, is it real or virtual? Okay. My image that I see on the screen is in front of the mirror. So the thing has to be real. Okay.
And it's projecting, which kind of indicates that it has to be real.
Cool. That makes sense. Okay, is it upright or inverted? My object has an arrow pointed upward, and the arrow is pointed to the right. My image, again, I'm not sure if you can see it or not, but the arrow is pointed downward, and it's pointed to the left. Guys, this is inverted. So your magnification is always going to be negative. All right. H prime. Positive or negative? Well, guys, I know it's going to be negative right off the bat. Now, I want to know the diameter. If I take my ruler, this is going to be a real strain for me to measure. So what I'm going to do is, I'm going to take a little scrap of paper, and I'm going to put it right on the screen. So that instead of projecting onto the screen, I'm projecting onto the paper. And I'm going to make a little tiny mark on one edge of the outer circle. And I'm going to make a little tiny mark on the other edge of the outer circle across the line. And again, I know it's low light. I'm not sure if you guys can see that I made those two little marks.
Sorry I was out of focus, guys, watching, but it's struggling with the low light.
Yeah, okay, so what I did was I made a little mark on the left, on the outer edge of the circle, Oops, I just moved the paper a little bit, sorry. And I made another little mark on the right. And again, I didn't use a big piece of paper. And please don't write on my screens. And then, I gotta chase the little piece of paper wherever it goes. And then, I take my ruler, and I measure. And guys, I'm only gonna give you one sig fig on this. It is 10 millimeters, or 1.0 centimeters.
Now, if I'm remembering correctly, the object was 2 centimeters,
It is 20 millimeters right across there.
and now the image is 1 centimeter.
So, if you look at your lab, oh, sorry, we're going to do m equals 2 different ways. One, we're going to do minus di divided by do, or minus 7.5 divided by 15, minus 1/2, 0.5. Or we're going to do the second way, m is going to be minus 1 divided by 2, minus 1/2. And the percent difference in m values is going to be 0% because they're both in. Okay, so what is f measured? Now it says that f given is 5. How do I know that? Well, beforehand I told you that there's a little sticker on here that says that f is plus 50 millimeters, the focal. 50 millimeters is 5 centimeters. So how are we going to get this f measured? 1 over do plus 1 over di equals 1 over f. So take 1 over 15 plus 1 over 7.5 and see if that equals 1 over 5. Okay. And then finally, do your percent error to the f values. So what I'm going to do next is I'm going to do a do of 25 and a do of 35, and I'm going to get the data for you, and I'm going to leave you for the calculations. First thing, I need a do of 25. So I'm going to take the screen off so I can see my numbers better. Do of 25, 25 minus 0 is 25. Next thing I'm going to do is I'm going to put my screen in, and I am going to try to get her in focus. Oh, wow. This one's going to be close. Close to the mirror. Teensy. Teensy tiny. Oh, wow. I think you got her, Dr. Johnson.
This one doesn't show up on the camera very well, but it is there.
Because it's blocked.
No, it's
No?
just we can't see the detail. It's flooded out by the light. But
Okay.
I believe that they'll take our word for it.
Okay. The ruler says 18.9, but that is not DI. My mirror's at 25, and my screen's at 18.9. What's the difference between 29 and 18.9?
25.
What's the difference between 25 and 18.9? Okay, I'm looking at this guy and the arrow is pointing down and the object is pointing up, and the arrow is pointing to the left where the arrow in the object's pointing to the right. You tell me if it's upside down or right side up. The image is in front of the mirror. You tell me if it's real or if it's virtual. I'm going to stick my little piece of paper in here. And I have 5 millimeters. I have 0.5 centimeters for a
Object or image height.
for the image height. Where the object height is 2.0 centimeters, this is 0.5. And that's the best I can do.
All right.
Okay, I think the last one that I'm looking at is 35 centimeters. So I'm going to take my mirror and put it at 35 centimeters, so the distance the mirror is to the object is 35 centimeters. Take my screen. Oh my, we are getting close and we are getting tiny. Oh, I'm glad I brought the reading glasses. I think that's the best I can do. Okay, I am at 29.4 on the scale. My mirror is at 35.0. So the DI is the difference between 35.0 and 29.4. We're getting small. Well, you know, I'm only measuring 1 sig fig here. I'm going to say 3 millimeters. This is, it's really hard to measure that. It's fuzzy, wow. And I only have 1 sig fig, which means I could easily get 10% error right off the bat. Okay, let's say 0.3. It's between 0.3 and 0.4. But I'm going to say it's closer to 0.3 centimeters or 3 millimeters. So let's see what else. Oh, other data, sorry. The arrow's pointing down, and it's also pointing to the left. In the objects, it's up and to the right. This one, it's the other way. And again, the image is in front of the mirror. Any other data? I think that's it. Okay, so we have done the mirrors. Off to the lenses. Lenses? It's much the same. If I take a look at the first converging lens here, the first DO was 50 centimeters. So I put my lens right at 50. Now again, I'm going to have an image. If I'm going to have an image, it's going to be over here. Positive for images is on the other side because light, I think, should go through lenses. Now what I'm going to do is I'm going to loosen the screw up and I'm going to move this back and forth until I get myself an image. And again, when the lines get really sharp, oh, but this is easier because it's bigger, it looks like. Well, maybe it's not bigger. But anyway, it looks really nice and sharp for me.
It shows up really clearly on the camera too. That's good.
Excellent. Okay, so I'm going to do that, and I'm going to shut that so we don't have that source of light there. If I take a look at where it is, that is 84.4. But that's not the number that you write down. We want the distance from the lens at 50 to 84.4. Okay, so the difference between 84.4 and 50. Good. Next thing I want to take a look at.
On your screen, folks, this red and green line there, that's the back of the light source, the object. So
The arrows. I don't know if you can tell on this one, but it's pointing down and it's pointing to the right. If I take a look at my object, it's pointing up. So this is an upside down image. Again, with lenses, is this a real image or is this a virtual image? Well, people, if I was here at a camera, could I take a picture of it? And the answer is yes. If you want to think about actually going to a movie where they actually project with film onto a big screen down front, you could stand in front of the theater and actually take a picture, and yes, you would be in the light in the image. So this is a real image. Okay, well, why don't we measure? And, you know, I think I might be able to use the ruler on this particular screen here. And I'm going to start one edge at 20, and my other edge goes to 21 and 1/2. So it is 1.5 centimeters across. Okay, cool. Now, what about the other questions? Oops, gotta use that finger. All right, so my H prime is gonna be negative, and it's 1.5 centimeters. Let's find out the magnification. M equals minus Q divided by P, or it's minus DI divided by DO. Well, 34.4 divided by 50, minus 34.4 divided by 50. I can't do that right off my, about negative 0.74, Dr. Johnson?
Somewhere in there.
Somewhere like that, okay, cool. And then M equals H prime minus H. Well, minus 1.5 divided by 2. That's about minus 7.5. Excuse me, minus 0.75, 0.75. So you are going to get percent difference on those M values. Well, what is your measured focal length? 1 over DO plus 1 over DI equals 1 over F. So 1 over 50 plus 1 over 34.5 equals 1 over, and see how close you get to 20.
Is that the, on the sticker? The sticker value is 20?
The sticker value is 200 millimeters,
Perfect.
which is 20 centimeters. Yes. Okay, next thing we're going to do is we're going to go to 40 for a DO, and then we're going to refocus. I'm going to get on this side and make sure I lined up perfectly. I don't think I did. I'm going to move this a second so that I can lean over. Yep, I'm off by a millimeter. Does it make a difference? This is physics. Okay, it's a little fuzzy, but it's bigger. Oh, fuzzier. It's kind of interesting how the smaller you get, the more focused you are.
For folks watching on the video, I am not changing the focus of this camera. That's actually the image changing its sharpness as it approaches the appropriate image distance for the screen.
Okay, I have ET 1.8. Now, again, that is not DI. My lens is at 40, so 81.8 minus 40. All right, measure. Oh, first off, arrows down, upside down. Images in front of the lens. Okay, now let's measure. So I'm going to put 20 on one edge. I get 22.2. So the difference between 22.2 and 20 is 2.2 centimeters, or 22 millimeters. And once again, the object had a height of 2.0 centimeters. That's all the data. You figure out the other stuff. Okay, let's go to 30 for a distance. Oh, fuzzy, fuzzy. I'll go inside and see what I can do. No. I gotta go. Oh, wow! Look at this. Further back. Oh my.
It's so cool when they come into focus like that.
Yes. There's little bit of wiggle room here where you could argue where it is in focus. I'm going to say right there.
That's
Okay.
cool. It's showing up really well on the screen.
Okay, so I have 90, I got 94.2. But again, that's not the DI. DO is 30, 94.2 minus 30. You can see the arrows pointing down. You can see the millimeter is upside down. Trust me, this is an inverted object. The image is in front of the lens, where it should be, okay? And let's measure. I'm going to put the 20 on the edge here, and I have 24.3. So 24.3 minus 20, 4.3 is going to be the DI minus 4.3 is going to be the DI. All right, now there's one more that they have.
So the image is actually bigger than the object in this case.
It is.
That's the first time that's happened, I think.
It is. It is. And yeah, if you do 4.3 minus or divide by 2, you're going to get 2.15. So that's more than twice as big as what the object is.
So if the magnification is bigger than 1, either the magnitude of the magnification is bigger than 1, either positive or negative, then it's a bigger image than the object. If it's less than 1, it's smaller.
That's right. It's a magnifying glass. Did you ever take an astronomy course?
A long time ago.
So you've seen like the pictures of the moon in the astronomy books.
Yeah.
Have you ever compared them to the moon?
No?
Because they're upside down.
Huh.
And the reason they're upside down is, what we can do is we can put another lens in here to make it go right side up, but you're going to lose some of the light. But the really good magnifications of the moon are upside down. And just by convention, they've always kept them that way.
I didn't realize that. Now I got to go back and look.
Now you got to go back and look. Okay, now the focal length here is 20. And the next thing they want us to do is put it at 10. So now the object is going to be inside the focal length. Now you remember when we did the mirror? There was a certain focal length of the mirror, and you had me and you were far away and I was upside down? And then when you brought me inside the focal length, I became huge and right side up? This is what's going to happen. I'm going to take this, I'm going to bring it inside the focal length. Okay, I don't see anything. Well, let's see where it focuses. I don't see it focusing anywhere.
Neither do I. Now,
Why not?
if I look through this,
Uh-huh.
I can see it. I can see
Oh my.
the object,
Yes, yes.
but it isn't projecting an image onto the screen.
No, because the image is back here. Can we turn this so the camera can see it?
I can move the camera.
Well, if you want to, whatever works. So this is a magnifying glass.
Let's see.
Should I raise it a little bit to get these things?
Oh,
on?
yeah.
More? Less?
I'm right on it. Oh, yeah, there it is. Look at that. So we're looking down the track. You can't see the track. All you can see is the circle that is the lens and the object behind it. And that's definitely right side up.
I'm going to go down a little bit so they can see the object. See how small the object is? And now,
Hey, hold on. I'm going to try
Oh,
to
I'm
get
sorry.
that both on the screen. Yeah, I can't. Well, there's the object. And,
do you want me to raise up again?
yep,
More?
nope. There's the image. So it's definitely magnified. Huh, cool.
So is there any way we could figure out that magnification? We know the focal length, right? and we know the DO, the distance of the object, we could figure out the DI. And the magnification is minus DI over DO. Yeah, we could figure out the magnification.
We can only do it one way this time, but we could do it.
We could do it. I mean, I don't know how we could measure the height of that image. I can't put my ruler on it. That's neat. Okay, now we had another thing to do, and this is working with two different lenses. All right, people, two lenses. Forming images using the converging lenses and diverging lenses. Now, once again, a converging lens is going to focus light to a point. A diverging lens is going to take light and spread it out. People who use glasses to help them see better use converging lenses or diverging lenses depending on whether they are far-sighted or nearsighted. Because either the light is forming ahead of the retina or is forming behind, the image is forming behind the retina. And we want the image to form on the retina. Okay, so two lenses. Number one, place an object a distance of 40 centimeters away from the converging lens. Well, what I'm going to do is I'm going to place the lens 40 centimeters away from the object. So this is positive 40. And what I'm going to do, number two, by moving the screen, I'm going to find the distance of the image from the lens.
What's the focal length of this?
This is the 200, positive 200 millimeter, positive 20 centimeter. Now this is the stuff we did last time for 40, and I'm hoping I'm going to find it somewhere around 82, because that's what we got last time, and I'm finding it at 82. I've got 82.4 this time. Is it upright or is it inverted? It's pointing down, so this is inverted. Is it real or is it, I don't think they're asking that. Well, this is a real image. Okay. Now, one thing that's kind of freaky is that the position of this image is going to be the odd position of the second object. Okay. The position. Not the distance or anything, but this location right here. Okay. So, oh, number three, measure the diameter. I can do that.
Since this image is going to be the object for the next lens, we need to know how big it is for the new object height.
That's right. Okay, and this again is 2.2 centimeters. We need to use that also for the magnification then. Oh, positive 2.2 centimeters, negative 2.2 centimeters. Since it's upside down, negative 2.2 centimeters for your DI1. So, place the diverging lens at a distance 34 centimeters from the converging lens on the opposite side of the light source. So I have a diverging lens right here, and at least I think I do. Okay? Yes, I do. And if I'm at 40 centimeters, and I want 34 centimeters away from the light source, then I'm putting it at 74. So this is the position of my second lens here. Okay. What is the, all right, calculate the object distance for lens 2. Okay. Now remember, the object distance for lens 1 was the distance the object was away from the lens. The distance for object 2 is the distance the object is away from the lens. We said that if the object was on, well, we can say the left side or behind the lens or whatever, it was positive. This is going to be a negative distance. Well, what is the difference between 82.4 and 74? Well, 82.4 minus 74 is going to be 8.4. So DI2 is negative.
DO.
Excuse me. DO2, thank you, is going to be negative 8.4. Okay. Now, by moving the screen, find the image distance. So what I want to do is, right now I've gone fuzzy. I want to make it sharp. Oh, this is neat. It got bigger and it got sharper. I'm going to shut this light source down. Oh, yeah.
That's so cool. Again, I'm not changing the focus on the camera at all. That's the image becoming sharper or fuzzier, depending on where the screen is.
I'm going to say there.
Look good to me.
All right. And I'm screwing that down. Good. Now the image is on the other side of the lens, so the Di2 is going to be positive. Okay, it's dimmer than before, yep, okay. Measure the diameter of H2. All right. Well, they probably want do they want Di2? Yes, they want Di2. And I am at 91.8. And again, what we're doing here is the difference between 91.8 and 74 is going to be Di2. Is the image upside down or inverted? Excuse me, is the image upside down or right side up? The arrow is pointing down. So once again, it is upside down. What is the height of it? Putting 20 on one side, and I have 24.5 on the other side, so my height is negative 4.5. Okay, now what we're going to do is we're going to calculate the magnification for M1. Then we're going to calculate the magnification for M2. Now this is really important here. M total is going to be M1 times M2. Now, this is the magnification of M total, your end product here. Got to ask you this question. The object is upright. The end product is upside down. Does that mean that M1 and M2 are both negative? What is negative times negative?
Usually that's positive to me.
Yeah. So it sounds like the only way we can have a negative is either M1 is negative and M2 is positive, or M1's positive and M2 is negative. So be careful of your signs. One of those is positive. One of those is negative. Okay. So what I want you to do is I want you to work with that. And then also, let's figure out the F of the diverging lens. It should be minus 15. But you know DI, you know DO, and let's see. Now guys, it says there that if you have more than a 15% error, that you should make your measurements again. Well, there's no possible way you can make your measurements again, because we did it for you. So tell us if it's a possible error. We did the best we can, but I'm an old guy. I use reading glasses. We'll see. Anything else, sir?
No, I think that's really good.
All right. You guys have a great day.